So, hello everyone. I'm hoping that you guys are having a nice time at today's fair. My name is Jeet Biswas. I work as a research assistant at Hochschule Darmstadt, and I'll be the host for you for this Science Slam session. Today's fair, I think, has been very technical and intense for all of you. So for this Science Slam session, we have a very light session, but hold your breath. We have some interesting talks lined up. So yeah, and some house rules is every speaker will have around 10 minutes to speak, and after a talk, you can raise your hand and can ask some questions. Okay, so let's start with our first speaker, Dr. Florian Stanovic. He's having a PhD and is currently working as scientist at Silicon Austria Labs. And Florian will be stepping out of the usual sensor and measurement conference menu and dive into something more flavorful. So buckle up for a multidisciplinary banquet. Florian with pole eating, a multidisciplinary feast.
So thank you very much. Also from my side, I really want to thank you for attending this session, because on the one hand, it's supposed to be, something smooth, something funny. But I tell you, and I think also all the other speakers are going to confirm this, it's in reality not so easy to present something like this, because we want to have a little bit of a scientific touch, but also being entertaining at the same time. So I would say it's a difficult task. But I was really very, very lucky this time, because for me, it was actually easier than I thought originally. Because the thing is, the abstract that I submitted at the conference, which is also a parallel session here, has already a little bit of an bizarre touch, I would say. It was namely about the topic of pole eating in magnetic systems. And then I thought, okay, pole eating, this is something. And I tried to present you this now in this Science Slam session as well. And so I did a little bit research, okay, how could I make this topic of pole eating to a Science Slam talk? And I found out really a surprising fact that the term pole eating, even though it may sound a little bit funny, if you look at very different fields and different scientific topics, then this is a really very well-known term. This was also to me a little bit surprising, and I'm going to present you now in my talk what is understood under this term in the different fields of science. I invite you now at the beginning already to think a little bit, what could pole eating be in several fields? For instance, we have here for Earth scientists. What may they understand under pole eating? A scientific writer, a biologist, a meteorologist, a mathematician even, some economist, some chef, political scientist, historian, or even computer scientist. So really take a few seconds and think, what could pole eating be understood in these fields? And before I forget it, I want to disclaim already a few images that I'm going to present in my presentation might be AI generated. Okay, I will now resolve this. Let's start with an Earth scientist. As you know, that the polar lights usually occur at the magnetic poles at the Earth. And they somehow, because it makes sense, the solar winds coming from the sun, they somehow approach the Earth from the poles. And this phenomena is widely understood as pole eating in Earth science. Thankfully, without any slurping or chewing noises which are going on there, which might be disturbing in the research of Earth science. Then the second one, as a sci-fi writer, of course, scientific writers and the author of scientific books, they always try to come up with somehow creative ideas that might illustrate some source of danger. And in this specific case, there was a writer who developed, let's say, a nightmare unfolds where wild magnetic poles begin to swallow up technology in the Earth. And they may start, for instance, at your personal Wi-Fi router. So also in this field, magnetic pole eating, a well-known fact. Then another thing, for biologists, as you know that birds flying through the Earth atmosphere, usually they use the magnetic field of the Earth for orientation. But as you might also know, that the magnetic poles, they slightly deviate a little bit through the Earth movement and so on. And in this specific case, it might happen that this confuses the birds and they suddenly cannot trust their own GPS instincts anymore. And this could, for instance, result in something that the birds have to adapt a little bit their eating habits. The next one is the meteorologist. As you know, the poles of the Earth, they are mostly unpopulated and there is quite some space. So the proposal of this researcher was to just place giant carbon sinks machines directly at the poles of the Earth. And they should eat up the CO2 and finally save the planet. I heard that this researcher is still waiting for budget approval for this fantastic project. Then mathematicians. Of course, you know or might know that poles are usually singularities in mathematical functions. And this mathematician, after several approaches, he developed an asymptotic absorption model that where one vector field basically eats up the other one. And yeah, I would say a deliciously complex topic. The economist, of course, you know that in capitalism, regions are competing to each other. And it might happen that one economic power basically eats up the wealth of another, finally ending up with complaining about inflation in the region. Then chefs are, of course, also very clever. They always try to find new dining trends that constantly emerge. And this specific chef had the idea to offer inclusive gourmet restaurants located at the Earth poles. If you do a reservation, be sure that you have a sledge dog team with you. The political scientist, of course, we know currently radicalization is quite present in today's society, unfortunately. And the trend that somehow political extremes are somehow consuming the middle ground is also called pole eating in this field. And finally, they are leaving us with not more than Twitter or X arguments in this case. The historical discoveries always bring quite surprising insights. And this historian really found an old manuscript that is predicting pole eating at the Earth. This was, by the way, written by a monk who also insisted that the sun was made out of cheese and quite delicious. And finally, the computer scientists, of course, data science and analysis are becoming increasingly popular in today's professional world. And the data clustering process, where somehow strong patterns consume weaker ones, is also referred as pole eating. Just a little bit like in the AI, but hopefully with less bias in the result. And finally, I want to tell you now what me as a magnetic researcher is understanding under pole eating. If you have a magnetic pattern with weaker poles between stronger poles, then somehow the poles are somehow changing the location towards the middle. This means basically these two poles are eating up the one in the middle. So with this, I want to thank you for listening to this presentation. I hope I could give you a little bit an insight in different fields of science. And finally, I want to ask you to visit our booth to discuss maybe more about the topic of pole eating. Thank you very much.
Indeed, multidiscipline buffet. And yeah, so does anyone want to have a question for Florian? Okay. Okay, then we will move to our next talk. So for our next talk, we have Mr. Martin Biswas. Martin Biswas has an interesting life. He manages the Go team of Kassel, which plays in the second Bundesliga. And he is also a member of the Church Council of Local Community and the board of the Literature House of Kassel e.V. Academically, Mr. Biswas has a degree in physics from TU Munich, and he has worked in various blue-chip companies such as T-Systems and Rheinmetall AG as software and hardware engineer. And in 2004, he started his own company, co-founded it. It's called Trout GmbH. And he started gradually moving towards the medical and automotive sector. And with his team, he has developed a new technology to classify the process data with the help of various methods in the field of AI. And today, he will be talking about secret whispers of cars and how we can decode their body language. Mr. Biswas.
Jeet, thank you very much.
You're welcome.
Good afternoon. Did you hear that? That's your car talking. You ever feel like your car knows something you don't? Imagine, you're cruising along, the engine's humming, you're singing to your playlist, and suddenly it's there, a noise. Not as dramatic as an action movie explosion, but subtle. A faint hum, a small rattle, a mystery whir, which was not there yesterday. You do what every reasonable person does. You turn up the music, pretend it never happened. You think it'll be okay, but guess it won't. Listen carefully. Your car is speaking Körperschall. That's structure-borne sound. But what is that language? Unless you are a suspension whisperer, you won't get the message. All you hear, and even worse, what you don't hear, is structure-borne noise. But your car is telling you something. It is telling, hey buddy, my wheel bearing is sore. And why the car is not talking human, it needs to be decoded. We have to translate the car's body language. You need a Babel fish to understand your car's vocabulary. I'm sure you have read Hitchhiker's Guide to the Galaxy. If you haven't, you have, please fix that immediately. Remember the Babel fish. It's a small yellow fish. Nowadays, it's a white fish swimming in the ocean under the light blue sky, resembling to the logo of my company. And if you stick it in your ear, or to be precise, if you install it on your computer, you will understand any language in the universe, or at least what your car is trying to say to you. No more mechanics who can only guess what's wrong. Your car speaks in many different frequencies. It's not French, it's not Klingon, it's like an orchestra. There are many oscillations shaking through your chassis, rippling in your shafts and bearings. But could somehow we translate these vibes, especially the bad vibes, we could tell which part of the car is going wrong, when and why. All we need is a structure-borne microphone. It measures sound and noise over the time. The bottom line is the timeline. The car moves from left to right, and it leaves noise over the timeline, a squibbly, chaotic line. Studying a raw waveform is like listening to a song, but it is a song for your car's ears, not for human ears. What you hear is only structure-borne noise, and it needs interpretation. Here comes the FFT, the fast Fourier transform. Here is our car on the bottom line, producing noise over time. And here is the FFT, taking the time domained sound, transforming it into frequency spectra. It splits the noise into its acoustic components and adds up the sum of the altitudes, of the intensities, and shows them here in this time slide window which moves with the car. Instead of chaos, we now have frequencies and peaks which show, for example, this is your driving shaft, this is your meshing gear. Oh, what's that? This is a high frequency wobble which needs analysis. And we have FFT which draws a clear picture. We now see it is the wing mirror which is making that creaky noise. FFT draws this picture of the musical components of the car, and it's only this triangle wing mirror which is broken, so no problem, keep on driving. Just math, but it feels like magic. FFT has been invented by geniuses who haven't been invited to much parties. We have here another, sorry, I have to check. We have another peak here coming up, which needs to be checked. And it is not only an additional sound. Your FFT analysis gives alarm. This is doomsday. Your rear differential is gone. Panic in about 3,000 miles. Because yes, your car really can talk. We can now transform mechanical knowledge into data. We switch from this is a weird sound to we transform, we plot, and we predict data. We do not react on problems, we predict problems. So welcome to predictive maintenance. All you need is test and reference data. We have reference data. It is the red curve. It comes from a car in perfect working order. We also need information of cars with known problems. The results of the FFTs are objected to a pattern recognition. And we see that these peaks in our reference data are okay, are normal. Which is not normal and is worrying is this big black peak in this data here, and we must take action immediately because we want to avoid consequential damage. Analyzing the sound of a vehicle means giving it a voice. And we do not want to wait until it is screaming. We listen when it is whispering. And we act before the frequencies get totally out of control and your car off the road, written off before tax, done and gone with it. At last, we repair things when necessary instead of replacing them on plan or suspicion. Everything in working order, all frequencies in perfect harmony. This was the story about Babelfish in engineering, to Fourier and the noises, and to all vehicles out there. Listen, have a good trip. Thank you and goodbye.
Thank you, Mr. Biswas. That was indeed an interesting talk, and it had mathematics and poetry also inside it. So, for our next talk, we have a fellow research assistant, Yannick Schick. Yannick Schick is a research assistant at Johannes Kepler University, Linz, Austria. He has master's degree in automotive engineering from University of Stuttgart, and after working in the field of electric powertrains in the industry, Yannick is pursuing his PhD at JKU, focusing on fiber optic sensing technology. I come from India, and megafauna has been my interest. And recently, human-wildlife conflict has been a big topic of discussion. So we'll hear from Yannick about the working principle of fiber optic sensing, which are helping track elephants near the railways in the forest in India. And also, it is being used in chemical process industries in modern factories. So Yannick.
Yeah, thank you for that kind introduction word. And I would like to directly start with the elephant in the room, and I do not refer to the contradiction within my title. I actually refer to that elephant here. And let us now consider that the room this elephant is in, that's the country of India, and within India there operates the Indian Railway that looks something like this, or it can also look like this, and like this. And when I was taking that trains back then, I didn't realize that they actually faced a problem. I stumbled across that problem during an online meeting later, where an Indian engineer was talking about the challenges they have, which arise from elephants on the train tracks. So these elephants just really hang out on the rail tracks, just like they have got front row tickets for a wildlife documentary. But the sad thing is, trains do not stop for documentaries. So what happens? They hit these elephants, and this is not good for sure, because the trains are broken and Greenpeace will be on the line again. So that raises a lot of concerns and brings up the idea to track these elephants actually before the train gets there. That sounds easy in the first place, because you think, okay, let's just take some sensor technology, but we are talking about 100 kilometers of railway. And they go through dense forests, so cameras would be really difficult to install with all the power supply they need. Drones, we need a lot of pilots to fly the drones. And a dense sensor network in that dimension would cost a lot of money. So we need a new idea to monitor that, to track the elephant. And this new idea is actually not magic. It's not a guy on a lookout tower with binoculars. It's fiber optics. And therefore, we just apply usual fiber optic cable to that rail tracks and monitor them. So this fiber is nothing special. It's just a telecommunication fiber. And it can actually give the train tracks a nervous system to track vibrations, to track the elephant stepping close by, waving its trunk, and so on. But you probably ask now how we get the readings from a fiber. So how actually is it possible to read vibrations from a telecommunication fiber, which usually just transmit the cat videos to smartphones? And that's where we have to introduce the topic of distributed acoustic sensing, or as the cool kids say, DAS, or DAS. And to understand the technology, we have to go small, we have to go really small, we have to miniaturize things. Maybe some of you know that picture from the children's book, The Little Prince, where the boa constrictor swallows an elephant, and all the adults don't see an elephant, they just see a head. I actually do not see a head in that picture. For me, it's more a laser pulse, a nicely shaped pulse of light. And we have to couple that laser into the fibers to get the distributed acoustic sensing running. So let's do that real quick. And as soon as we do so, this laser pulse just travels down the fiber. And due to the manufacturing process, we have, even in normal fibers, we have inhomogeneities. And these inhomogeneities scatter the light back. Let's slow down things a little bit. It should be a little bit slower now. Yes. So you see, at each inhomogeneity, there's a backscattering. It's the so-called Rayleigh scattering. And that creates a footprint of the fiber, which stays stable as long as there's no distortion alongside. Now let's add some distortion to the fiber. Let's add some vibration patterns. And what happens, that actually these vibrations tiny little bit change the length of the fiber, the refractive index of the fiber. So the light which is gathered back from this inhomogeneities changes. And actually what changes is the phase of the light. So we have phase shifts in the light backscattered. And to read that all from the fiber, we need a specific device, because right now we're just having an effect in a fiber which helps us nothing. So we have to build a so-called interrogator. And I quickly sketched it up here. It works based on a continuous wave laser. The laser has to be narrow line because we are a little bit picky, and otherwise it would also not work. And by adding some fancy optical switches and acoustic optic modulators, we can create these pulses which we need, because I just showed you. So we send these pulses through the circulator. This is like a security guard just deciding which direction the light takes. So it sends the light pulse in. And the backscattered light is sent to an optical detector. And this optical detector can compare the initial laser to the backscattered light. And that's how we can get the phase with a little bit of math. So actually, these inhomogeneities happen in a much larger scale as I can display here. So we also have a really good resolution. It's not just a measuring point every meter. It's like continuously throughout the fiber we have that inhomogeneities. And by that, we build kind of a radar-style topology. We pulse in a light, and we get the backscattered light, which has phase shifts accordingly to the vibration patterns, and we can just read. Okay, so I know the technology, you know the technology now, and I attended that meeting where we talked about elephants, and I was really inspired, and I thought there have to be some equally novel application in Austria. And I thought, okay, let's call my colleague Guilherme in Brazil. He's a true expert. Let's just have a discussion where we can use that technology in Austria. But I was not even able to talk a lot because he was really excited. He was telling me, oh, we finally did it. We are able to track whales in the ocean, the vocalization of whales. Okay, whales. Meanwhile, I'm in Austria and no one seems to be interested in some mountain goats jumping from rock to rock. So I was kind of devastated. And I started to think, and then I realized what we have in Linz, in Austria. We have a lot of industry and a lot of chemical industry. We have the first Alpine steel manufacturing. And actually these chemical plants, they also have a heart, like the chemical reactors. It's kind of the heart of that industry. So I just took the picture of one of these reactors here to give you a better understanding what actually happens inside if we use an easy type. We have some liquid and we spark some gas from the bottom. And through the mixing process, they can interact, and that's what we want. If you want to simulate it, just go to the bathtub and fart. Then you have not a column reactor, but at least you have a bubble reactor. Okay. So, and the idea now is to sense the vital signs, not of animals, but of these elephant-sized reactors. And to do that, we need to press our fiber optic stethoscope to the metal wall of that reactor. Just like a doctor hearing the heartbeat, we want to hear the heartbeat inside that reactor to characterize whether they are healthy, whether they are working properly. And if we do so, we usually start in a laboratory style, so our reactor is not that huge, it's just a laboratory style reactor that size, and we wrap the fiber around. And I will quickly undress this reactor for you to show you what happens inside. For example, we can sparge in a gas and we have a large bubble moving. Okay, so enough nudity, so let's have a look on the results. So what we actually see with our fiber optics is the bubble rising. You can see the formation process. So this is actually the length of the fiber. This is the time scale. So first the bubble is created here, the sparge, and then it rises. So at least we can see sound now, what I promised in my title. And I also promised you that the light can hear something. So let's apply our stethoscope again. And we can also hear the creation of that bubble. Similar to probably an elephant walking, you can really hear this explosion when the bubble is created and slowly racing through the reactor. So, all in all, I proved that we can see sound, that the light can also hear, and in the end, we are still saving wildlife because while we track these reactors, we can optimize the processes and we can probably reduce the carbon footprint of these chemical plants, and that will help all the animals in the world. So I think it's a noble application which we follow. Thank you.
Thank you, Yannick. That was really insightful talk. And I hope you get success in your PhD and we can see this application in wildlife and also in industry.
Thank you.
Okay, so our last speaker is Mr. Ante Janevita. So for our last talk, we will travel to Scandinavia. Mr. Janevita has entrepreneurial interests, but right now he is working in the physics department of the Aalto University, where they are developing sensors from plants. So it's going to be another interesting talk. So Mr. Janevita.
Thank you. All right, thank you, ladies and gentlemen. So today's topic will be wood-based nanomaterials in gas sensors. And so my name is Antti Jäänvirta from Aalto University. Can you raise your hand if you've ever heard of Aalto University? Two hands, okay. Yeah, not the best of names that combine, but it combines universities of technology, business, and arts design all come together. And I work for a project called Smart Sustainable Gas Sensors. It's a research to business program for the next 1.5 years, supported by Business Finland. So have to give my thanks to Business Finland as well. Okay, so then what is Finland? People don't normally know much, but the first thing you need to know, Finland is a forest. So 75% is covered in forests. So for us, wandering around in a forest, it's not a hiking hobby, it's not an emergency, it's your everyday commute. And on top of that, we have 100,000 lakes because, of course, the trees need something to drink. But we are one of the world leaders in wood-based products, that I can say. So this was an invitation for young scientists, so I'm not that much into science, and as you can see, I'm not exactly even young anymore, so let's at least hope that I produce a slam in the end. I don't have much equations or graphs, but I want to tell you a story instead of something that lives in the woods. I love to make comparisons, and there is something in the woods that has astonishingly many similarities to a sensor. And I will just give you a warning if anyone is afraid of spiders, so I will soon show a picture of a spider, but don't worry. So sensors are a lot like spiders. They are almost always hidden out of sight. They are a little bit intimidating maybe. Also sensors, because they are so deep tech, they intimidate a lot of people. And biologists say that we are never more than 1 meter from the nearest spider, and that's pretty much true also for sensors. And spiders consume 400 million tons of insects that would otherwise carry diseases to us and our life, our food and everything. So they really also, just like sensors, they save lives. But what is really astonishing about the spider, it is perfection in detection. It has in different legs different types of sensory hairs and elements which enable it to pick up different signals from the one and the same event. Why it doesn't have to move around or look around to see what is happening in its web. So basically, from different pairs of legs, it gets different signals. And from these signals, it creates this extreme selectivity that without moving, without looking around, it can know, does it have a small prey? Does it have a large prey? Does it have a dangerously large prey that could end up killing it? Or is it something that is of no interest to it, like a raindrop or a wind breeze, or even if it's a potential mate? But how does it do that? Because all these signals, they are just signals flowing around, and the answer, of course, is the brain. Now, the spider brain is not a fancy one. It will never compose a symphony or read poetry, but this selectivity it does into perfection. Which brings now us little by little to our sensor. This is only one wire. I will soon show you more. But this is what I also have in my pocket with me. I can show to you and make a demo if you are interested. So it is wood-based materials that are printed, and they can be printed either on paper or polymer, and they are chemi-resistive, so they react to a surrounding gas by changing the resistance. But if we take several of these made from slightly different compositions, start to look familiar like the spider, 4 signals with different colors, and then we connect these into a brain, which is the machine learning algorithm. And all of a sudden the magic happens, and we see gases with high selectivity. But the similarities are far from being over. Oh, by the way, yeah, this it's a continuous measurement. One of the questions I always get asked, that is it continuous or just single use? It's continuous. But the similarities are far from being over. For example, you would never need to heat the spider to 300 degrees for it to work, like you do with many gas sensors. A spider doesn't necessarily have to eat in a month, so it's extremely low energy consumption. You don't need a clean room to produce spiders, and you don't need a clean room to produce our sensors either. And I've never heard of a spider that requires calibration, so neither does ours, because it has the brain that can fight the drift and compensate. And yes, it does also recover after experiencing something. And then when the poor little spider expires, you know, in Nomen Patris, Filii, Spiritus Sancti, so on, you do not need to bring out a toolkit and a soldering iron, and neither do you with our sensor. You can have just a piece of adhesive that you take out with your fingers or pair of pliers and stick in a new one. And what we have is just like a spider, 100% biodegradable and recyclable. Of course, there are differences. I've never heard anyone of patenting a spider, so we have patented our technology. So there is 15 quadrillion spiders in the world, 25 million tons of them. And this compares to 100 of the world's largest cruise liners, Oasis of the Seas, which, by the way, is built by German company Maya in Finland, in Turku shipyard. But yet, everyone is concerned of the sustainability of these cruises, but I don't hear anyone concerned over the sustainability of spiders. So now, in the future, when we will have millions of gas detectors, we will no longer have to worry about the sustainability. So a quick recap of what we are doing. Printable, machine learning driven. With one only, you can detect 5 to 10 gases with really low power in ambient temperature, without calibration needs, easy to replace, biodegradable, and recycled easily. And here comes a little bit of the slam, I hope. We have currently the capabilities for these 6 gases starting from 1 ppm, and we are building a library of further gases, and we are hoping that in a little more than a year and a half, we will have a commercial spin-out company from the university over this innovation. So I'm basically here to do a little bit of market research and to also hopefully hear your ideas, because I have been working for this for a very short time. You are the experts compared to me, so love to meet you afterwards and discuss that, what this could be used for, and hopefully to find some testing partner companies or universities, and well, it wouldn't hurt if there's some investors around. Okay, so thank you. The next time you see a tree, or you see a spider, or you see a cruise liner, think of the crazy guy from Finland with the gas sensor. Thank you.
Thank you, Ante. So that was a really interesting talk, and spider has been my interest for a long time. I had one spider in my room for a long time, so I was definitely living closer than 1 meter. So yeah, that's all the talks that we had today. I hope all of you had a really nice time and a relaxing session. So we'll see us again in our next edition of Science Slam. So thank you all.